So this is the limit you're going to end up working with. In a lot of these problems, the two we did in class, we were finding like f prime of x at a equals 3 or at a equals 7 or at some special number. And so we weren't having just a generic x in here, we were having a number in place of the x. That's fine. Whether we have a number in place of the x or we just do it in terms of x, the process is still going to end up the same way. It always feels a little scarier when you don't have a number in place of the x. It just feels a little weirder. And you're not sure exactly what's going to happen. First thing you have to do, x plus h into the function for x. This is just your function in terms of x. F of x plus h minus f of x. If you tried to evaluate this limit right now, you get 0 over 0. All limit definitions of the derivative are 0 over 0. All limit definitions of the derivative require algebraic manipulation. In this one, oops, switch over. When I square x plus h, it's going to look like that. X plus h quantity squared. If this was x plus h quantity cubed, it would take a little bit more time to expand that out. If it was x plus h to the fourth, x plus h to the fifth, you can see where if those powers got really big, this would be kind of a pain to do. But the good news is we're going to find out that there's a shortcut, and so even if it is a cube or a fourth or a fifth or a sixth or a 12th or an 18th power, it'll be fine. We won't have to do it this way, but we can still find the derivative function. If I left my h off of that, didn't I? X squared plus 2xh and then distribute. So 4x squared plus 8xh plus h squared minus 4x squared all divided by h. Oh, I do need the 4, thank you. 4h squared. Okay. If you remember when we talked about this on Friday and we did this with a problem where we had the number instead of an x in it, at this step, the constants added out to 0. In this case, the x terms are going to add out to 0. Basically, the thing that always happens is anything that doesn't have an h adds out to 0. 4x squared, negative 4x squared, add together with 0, only things with h's are left. If this had been at like 8 and x equals 3, bless you, then I would have a number here and I would have a number here. These guys, this would still have an h, this would have an h, that would have a number there, but times 8h. These two things would still cancel out. So this is the limit as h approaches 0 of 8xh plus 4h squared, all divided by h. What happens at this step? You can take an h out of both, yes. This should happen all the time. When you factor an h out of both the numerator, well, and you can't factor all the time, but when you factor the h out of the numerator and divide that away, and then take the limit, we get 8x plus 4 times 0 or just 8x? If you didn't practice Okay. If you didn't do any of the homework that had you practicing this, you should do that. Okay? I keep saying it's like not super important, and it's not. It's not going to be make or break, but it's also not something that you should just throw away. You can do these problems. The problems on your homework had you practicing kind of two different things, two different techniques, two different limit definitions of the derivative. Now, all of that work to get 8x. Power rule will get us there. Did I print that over yet? Nope, I don't think so. That's okay. Power rule will get us there even faster. What power rule says for finding derivatives, and I'll pull up the actual sheet in a minute. Power rule says if I have any polynomial term x to the n then the derivative in terms of x is going to be n times x to the n minus 1 power. After doing, probably didn't take too many, but after doing several polynomial problems with the limit definition of the derivative, Isaac Newton realized the same thing always happened. If he started with a quadratic function, he got a linear derivative. If he started with a cubic function, he got a quadratic derivative. The derivative he got was always 1 degree smaller than the original function. And there was this extra coefficient thing that happened. So based on power rule and one additional rule that says if you've got another k right there, another number, that you can just have that additional k in there. When I have 4x squared, then y prime, or my derivative, is 2 times 4 times x to the first power, or 8x. The power rule is one of our best friends. The power rule means that we don't have to do limit definition almost ever again, because power rule shortcuts that entire situation. Let me print this over real quick. Alright, and it's over here. Doop de doop doop doop.
Yes, so exciting. I'm so glad. How many of these formulas do we have?
How many formulas? Total for derivatives?
What do we have to learn?
I don't have a count. Probably it's like 11 or 12. Okay. Okay. So, I just kind of showed you power rule, and I shoved constant multiple rule in there. You don't need to know the names of these things. You just have to know how to use them. Power rule, if you have f of x is x to the n, then the derivative is going to equal n times x to the n minus 1. If you've got an extra constant multiplied by your x to the n function, that constant will just get multiplied by the derivative. So in another example, if I took these two rules together and I said, okay, everybody, my f of x is 7x to the 4th power, what would f prime be? What would be my derivative?
28x.
That's right, 28x to the 3rd. And if I wanted to do it with the limit definition of the derivative, I could. Who wants to do this? Nobody. And I'm not going to. But if I wanted to, I could do the limit as h approaches 0 of 7 times x plus h to the 4th power minus 7x to the 4th, all divided by h. I'd have to expand that to the 4th power. I'd have to combine the terms. I would have to factor out the h, and then I would take the limit, and after all that happened, this would be the result. I like this way a lot better than that way. Okay? Not that this can't happen. It's because of this generating certain patterns that we get to shortcut it. 2 more shortcuts, and we're basically in the position to take the derivative of any polynomial, not just a monomial term, but any combination of monomial terms. Because we also have the sum and difference rule that says, hey, if you've got a sum or difference of polynomial terms, the derivative will be the sum and difference of the derivatives. So that means if I had y equals x cubed plus x squared, my derivative would just be the derivative of each of those terms individually, 3x squared plus 2x. Once again, I could do the limit as h approaches 0 of x plus h quantity cubed plus x plus h quantity squared minus x cubed minus x squared, all divided by h. Expand, 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 combine, 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 factor out the h, blah, 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 blah. That's what you would get. My college professor made us to do like 20 of them before he taught us power rule. I only made you do like about 5. Okay, so power rule shortcuts everything. Sum and difference of terms, hit the derivative on each of them. Only 2 other pieces we got to deal with that would be weird. One is when you have a constant. If you just have a constant piece, the derivative of that constant piece is 0. That kind of makes sense if you think about it as a slope, that a derivative is just a slope. If we have a function like f of x equals 4, which is a horizontal line through 4, the slope of that horizontal line, the slope of any horizontal line is 0. F prime of x for x equal 4 would be 0. The derivative of a constant is always 0. All right, so stop for a minute and see if you can write the derivative for this 6th degree 5-term polynomial. 5x to the 6th minus 3x to the 4th plus 2x cubed minus 8x squared plus 17. What would the derivative be? If we ran the limit definition of the derivative, what would the derivative function look like? Usually if you ask people what they remember, if they took calculus and you ask them about derivatives, this is usually the thing. They usually remember a power rule. Okay. Okay. Now, we're going to use the word derivative two different ways. Sometimes when we talk about the derivative, we'll be talking about the derivative function. If I give you a function in x, you can give me a derivative function related to that function also in x. So typically you know that that's what you're being asked to do. If it says, hey, given f of x equals this, find f prime of x. This means I want the derivative function. I want the derivative what you would get for the derivative in terms of x. I want what you would get if you ran the limit definition of the derivative with x. If I want you to find a value, I'm going to ask you to do that slightly differently. And example 2 is a perfect example of that. Example 2 says, find the slope of the tangent line f of x to f of x at x equals 1. Slope of the tangent line means use a derivative. So I want the derivative of f of x at x equals 1. Or I want to find f prime at 1. Okay. Now this is about the only negative, and it's not even really a negative, but if I want f prime at 1, I still have to find f prime of x first. I can't do both at the same time like the limit definition will do. The limit definition, if I said find me the derivative at 3, you could run the limit definition with a 3 in there and pop the answer out, pop the number answer out. If I want the limit, or if I want the derivative value, but I want to use shortcuts, f prime of 1 first requires f prime of x. All right, so here's f of x, and we're going to run into one more little shortcut, or one more trick here. 3x to the 4th minus 5x plus 2. My derivative would be 12x cubed minus 5. Let's make sure we're all okay with where the 5 came from. You all right? Are we okay with how power rule of 5x leads us to 5? You might be like, I don't know. Okay, so if f of x is 5x, or 5x to the first, when I hit that with a power rule, that would be 1 times 5 x to the 0. X to the 0 is equivalent to 1, and 1 times 5 times 1 is just 5. Another way to think about that, if I gave you this, and I said, what's the slope? What's the slope of y equals 5x? 5. Lines have one slope. They have a fixed derivative. Any line slope, its slope is also technically its derivative. So that whole time we were talking about y equals mx plus b, the m value was the derivative of that linear function. It's the slope of the line. The cool thing about a line, though, is its average rate of change, the slope between 2 points, and the instantaneous rate of change, the slope at 1 point, it's all the same. A line has one slope. Curves have different slopes at different points, and average rates of change and instantaneous rate of change are going to be different in different places. If you've got a line, you got one slope. That's why we started talking about lines, because they have one slope, one rate of change. So the derivative, the slope of a linear term, is just the coefficient of that term. The derivative of 5x is 5. The slope of 5x is 5. So my derivative of 3x to the 4th minus 5x plus 2 is 12x cubed minus 5. So then s prime of 1 would be 12 times 1 cubed minus 5, or 12 minus 5, which is 7. All right, how are we feeling? Yeah, power rule is great. Power rule makes everybody, like, limit definition, you're like, oh, this is going to suck. And then power rule comes, and you're like, yay, I love you, power rule. Yay. All right, do number 3. And then see what you can do on number 4. You're going to have to put some pieces together on number 4. I will write something down to remind you a little bit about number. We did a problem like number 4. We kind of did it. We started from the slope part. Start with number 3 though. Instantaneous rate of change at that quartic function when x is -1. And then write me an equation of a tangent line. And I would suggest writing it in point slope form. Right, so instantaneous rate of change is just derivative. It's just slope at 1 point. And we've got the derivative shortcut of the power rule to help us. So we don't have to throw anything in the limit definition of the derivative. All we got to do is generate the derivative function and then use that to find my derivative value. Think about power rule of each piece. If I want the derivative of this whole polynomial, that's the fun thing about polynomials. The derivative of the whole polynomial is the derivative of each piece put together.